Hi, this is a tutorial on the Quine McClusky or the qmc method, and we're going to talk about a Petrick coverage. Our starting point for both the Quine McClusky method, or the QMC method, and with Karnaugh Maps is a truth table. And in both, our first decision is whether to look at the mini-terms or the maxi-terms. So let's choose to look at the mini-terms, or the ones. Over here in the Karnaugh map, we'll be looking at this don't care, this 1, this 1, this 1, and this don't care. In the QMC method, what we do is we cross out these rows we're not going to use. The rows here with zeros on them. And then what we do is we count the number of ones in the inputs. So if we look at all three of these zeros, there's 0 ones. Here there's 1 1. Here there's 2 ones. Here there's 2 ones. And here there's 2 ones. In summary, after inputting the Karnaugh map, the first step in the QMC method is to get rid of the zeros, where the output was a 0, these 3 lines, and then count the number of input ones. This is what we're left with. The next step in a Karnaugh map is to begin circling implicants of 2 mini-terms. We can see one implicant of 2 right here. We can see another one of 2 right here. And then we can see another one of 2 right here. And we see that this guy is all by himself. What we have to be able to do is the same thing in the QMC method. So the way we do that is a couple of steps. But the first step is to figure out how far away these are from each other. If we look at this one and that one, they're 1 bit change away. Y is changing to go from here to here. To go from here to here, W is changing. To go from here and wrap around, X is changing. There is a 1 bit change. So the purple is a 1 bit change in X. So the reason we counted the number of input ones is to automate this process. So what we want to do is we want to compare all the zeros with all the ones. We just have 1 0 and 1. And then we want to compare all the ones with all the 2s. And this way we check mechanically every single mini-term, right? Each of these rows right here is a mini-term, to see if it's 1 bit change away from another mini-term. So how would we do that? The whole purpose of these arrows is to make sure we compare every mini-term with every other possible mini-term. So we want to keep track of the mini-terms that we're comparing to see if they can be combined into a 2 mini-term implicant. So we're going to start off with this comparing 0 with 2. Right? They could possibly be a 1 bit change away. 0 and 2. All right, yes they are. W stays a 0, Y stays a 0, and only X changes. So we don't write down W bar and Y bar here. Instead we write down 0 dash 0 in the QMC method. All right, now we're going to compare row 2 with row 3. Row 2 has one input that's a 1, and then row 3 has two that are 1s. So there's a possibility there's a 1-bit change. And thus, yes, there is. So 2 and 3 stay the same. W stays the same. W stays a 0. X is a 1, and Y changes. So we're comparing rows 2 and 3. W stayed a 0. X stayed a 1, and Y changed. Now we're going to compare row 2 and row 5. Row 2 and row 5. There's a 1-bit change. There's a 2-bit change. There's a 3-bit change. So 2 and 5 cannot be compared. They're prime. We're trying to compare 2, 0, 1, 2, 3, 4, 5. We're trying to compare 2 with 5, and that's a 1, 2, 3-bit change. So 5 turns out to be prime. We'll check that coming up a bit more. Now we're going to compare row 2 with row 6. Miniterm 2 with miniterm 6. Miniterm 2, W is changing. X is a 1 and Y is a 0. So it's a dash 1, 0. Now the QMC method is sometimes called the method of primes because at each one of these stages you have to harvest your fruit. You have to harvest the primes that you found. 0 and 2, miniterm 0 and 2 combine to form an implicant of 2, so they're not prime. So row 0 and row 2 are not prime. Miniterm 2 and miniterm 3 combined to form an implicant of 2. So row 2's not prime and row 3's not prime. Row 2 and 5, well, this is a possible prime. We don't know for sure yet. We have to go through this check in the QMC method at the end. 2 and 6 successfully combined to form an implicant of 2. So 6 is prime and 2 is prime. Now we're done. These are all the implicants of 2 that we've found. And 5, row 5 is prime. So this 1 is all by itself, which is the same as this 1 being all by itself. So now let's do one final comparison with the Karnaugh map. This 0 dash 0, X is a 0. Don't care about X, which is a first value, and Y has to be a 0. So that's, this one is this 2, this purple 2 miniterm implicant. Which one is this? All right, so it's not W, so it's on this row. X has to be a 1. X is a 1, and it doesn't care what Y value is. So this one is the gold one. All right, what about 2 and 5? Oh, we couldn't do that one. That one didn't exist. Remember, we tried to go 1, 2, 3-bit change. So that's why we couldn't do it. So this wasn't really an implicant. What about 2 and 6? Well, W doesn't matter. X is a 1 and Y is a 1. So this implicant right here is this green one. So step 3 is to sort these miniterms and compare all the 0s with the 1s, the 1s with the 2s, the 2s with the 3s, the 3s with the 4s, the 4s with the 5s. If you have 32 inputs, that could go on for a while. And you're looking for parties of 2. You're looking for primes afterwards. So this is a summary of all the things we did up here, and here I've rewritten what we did. So let's see. 0 and 2 are covered, yeah. Those are the mini-terms. The row 3, mini-terms covered. This was actually a 3-bit change, but really you just want to record 2 or more bits are changing because you can only have 1 bit changing. 2, 3, 4, 10, 15, that's not going to help you form an implicant. So yeah, in actual fact we had a 3-bit change right here, a 3-bit change. Yeah. So the next step is to compare all the 2 mini-term implicants to see if we can combine a pair of them to form a 4 mini-term implicant. So the step is to essentially create a new truth table. So we have a W, X, and a Y again, but this time we're writing down the implicant in this form. That's why we chose this crazy form in the QMC world. So instead of writing not W, we write 0. Instead of just not mentioning X, we put a dash. And then for Y, we would not, instead of not Y, we write down a 0 right here. So that's this row. And then this row, 0, 1, dash. And then we skip this one because we couldn't form an implicant. And then this one, dash, 1, 0. Now the way we check to see if 2 implicants can be combined is by looking at the don't cares. That's why we expose the don't cares right here. And we can't combine any of these implicants. Well, obviously you can see from the Karnaugh map we can't combine these implicants. But the rule, or the rule of thumb that you're going to see evolving in the next slides is we can combine them if they have don't cares in the same column. But right now that is a don't care, but there's no other don't cares in the X column. There's no other don't cares in the Y column. So we can't combine these. These are all prime. These are all prime. All prime. So in summary, the next step in the QMC method is to compare the 2 mini-term implicants with every single one of them with all the others to see if any of them can be combined to create a 4 mini-term implicant. And in this particular case, we couldn't because they're all prime. So we now revert back to the traditional Karnaugh map notation, not W, not Y, not W, not Y, not WX, X, not Y. Our next step is to do what's called a Petrick cover analysis. That's where we look at all the possible combinations of circuits that could be built and choose one of them. So we have to start off by redrawing one of these mini-term tables. So let's redraw this one. 0, 2, 3, 5, 6. 0, 2, 3, 5, 6, X, 1, 1, 1, X. So it's 0, 2, 3, 5, 6, and then the output was X, 1, 1, 1, X. So W, X, and Y were 0, 0, 0, 2, 3, 5, and 6. Now what we do is we write down all of our primes. So we've got a prime up here, which is W, X, bar, Y. We've got a prime right here, which is W, bar, Y, bar. It's a prime implicant. This is another prime implicant, W bar X, x, y bar. Now we don't need all of these implicants. So we're just trying to figure out which ones are necessary to build a circuit, or what the alternatives are. Now we go through and we go, okay, this one covers just that 5. That's it. This one, wherever w is a 0 and y is a 0. W is a 0 and y is a 0 right there. W is a 0 and y is a 0 right there. Okay. Here's where w is a 0, x is a 1. Let's see. W is a 0, x is a 1. W is 0, x is a 1. Here and here. Here's where x is a 1 and y is a 0. X is a 1, y is a 0. X is a 1, y is a 0. All right. Now what we do is we do a coverage. We look for these mini-terms right here, which are only covered by one of these guys. This one right here is only covered by that check mark. There aren't any other check marks, so we have to use that in our circuit. This one right here is only used by that check mark right there, so we have to use this in our circuit, and it happens to also cover this one. So we're done. We did not need to use this implicant, and we did not need to use this implicant. So our final circuit here, our function of w, x, and y is w x bar y or w bar x. So to wrap things up, let's compare with our Karnaugh map one more time. This was a summary of the Petrick cover right here. So you can see I've just typed everything here that I drew. Okay, so that's a summary of the Petrick cover process. And now let's just look at our final result right here. What implicants will we use if we did this just using a Karnaugh map? Well, we'd say, okay, let's just circle these two and this one, right? So there's your mini term, and there's your implicant of two mini terms. Yeah, so the QMC method does work. Seems a little bit longer, but our goal is to write software to do this. So we're trying to tease out all these steps.